Section 15.6, Applications of Equilibrium Constants. This is a pretty simple section. There's a couple kind of hard math problems in it, but the concepts are very, very easy. The only problem is going to introduce a new letter, and it just makes everybody think that it's hard because there's all these letters that you have to keep straight. If you remember that the equilibrium constant, which we called K sub C, is going to be equal to the concentration, molar concentrations of the products, so let's say that's C, raised to whatever coefficient that is, times, if there's a second one, then it would be the same, divided by the concentrations of the reactants. So let's say that's A, and maybe there's a second one. It doesn't matter, okay? Now, we know that C and D are products, and C and D, if that number is big, then your K sub C is big, then that means that you're making lots of products. So at equilibrium, when all of the stuff stops changing, and you have the same amount of products and reactants in the jar continuously, then you look at your K sub C, and if it's high, then you know you're making lots of products. If it's low, you're going to make lots of reactant. Okay, you can use stoichiometry, as we've seen in the past, to find K sub C, even if you don't know it all at once. But there's another very useful one that if you don't, let's say that you are running an experiment and you're not you don't know what equilibrium is. You don't know how long it's going to be to equilibrium is reached, and you take some readings. You can use those readings to tell yourself, am I there yet? Am I at equilibrium? Okay, we're going to use the same equation, only we're going to call it Q. Q is the reaction quotient, and we're going to treat it exactly like K sub C. Okay, so that means it's going to have exactly the same setup. You're going to put the concentration of C, put the concentration of D, raise it to the D power, concentration of A, raised to the A, concentration of B, raised to the B. The only difference is that these numbers, these concentrations, are all at equilibrium. And these are at any time. Okay? So I have no idea. I'm just going to let it percolate for a while and sit for a while, and after a while I'm going to take a reading. And I don't know what exactly I am, but I can measure Q, I can measure K, and then I'm going to compare Q to K. And then that comparison will give me some interesting things. So if you compare Q to K, and remember it's set up exactly the same way, the expression's exactly the same, except that K is the numbers at equilibrium, and Q is just readings that you made, your measurements that you made. Okay, so there are three possibilities. Either Q is going to equal K, Q is going to be less than K, or Q is going to be more than K. There's no other possibility. If Q is equal to K, and K is the equilibrium constant, then it must be at equilibrium. So if you take a reading, if you've calculated what your K should be mathematically, then you take a reading and you make a measurement, and all of your things are exactly the same as K, well, you just stumbled upon exactly the moment when everything was exactly equal, when the rates were equal, when it was at equilibrium. Okay, chances are that's never going to happen. But if it is equal to K, then if Q is equal to K, then you must be at equilibrium. Okay, if Q is greater than K, then at the moment I've got too much product, and I'm not at equilibrium yet. Okay, it's moving towards the left, so the products are being broken apart into reactants. Okay, or in whatever way it's proceeding. It's moving towards more and more reactants. So it's not, if Q is bigger than K, then I've got too much product and too much on the right. Okay, so I just always think of it as K followed by Q, okay, king and queen. And if Q is bigger, okay, if Q is bigger than K, then it must need to go to the left. It's moving from products to reactants. So it hasn't reached equilibrium yet, and it's going to be heading towards the left. It's moving towards the left. It's moving towards more reactants. If I have a situation where Q is less than K, okay, so I always put it the same way, Q, King, Queen, Q is less than K, well, then what's going to happen is I've got too much reactance. I've got too much, got too much reactance, and I'm going to move in order to equalize. Remember, K and Q need to be the same. So I've got too much on the left, I've got too many reactants, and so it's going to move towards the right, towards making more products in order to get to equilibrium. So if you have a situation where your K is bigger than Q, then it's going to move towards the right, which is more products, okay, in order to get to equilibrium. If you have a situation where Q is equal to K, then you're at equilibrium. If you have a situation where K is less than Q or Q is bigger than K, then then I've got more products than I need, and it has to move backwards in order for Q has to go lower in order to get equal to K. And so the products are going to be made into reactants. You can see that there's not much here in terms of mind-numbing hard stuff. The only problem I see is that it's another letter and it makes it feel harder than it is. But it's actually pretty useful if you're given measurements to know whether you're at the end or not. You don't know exactly how long it's going to take if you've never done it before. You don't know how long to sit and wait. If you take a reading and it's not equal to K, you just keep waiting and it's not done yet. It's just basically like a kitchen timer.